It's my pleasure to welcome at this seminar Jonas Pfeiffer from the Technical University of Darmstadt. I think some of us know him from some recent conferences, and so we are looking forward to what you can say about possible, with a question mark at the end, a new paradigm for transfer learning. So the floor is yours, please.
Yeah, thank you very much for the introduction. And I'm excited and honored to give a talk about my recent work here. Yeah, so what I'm going to present today is basically some work that, more or less the PhD work that I've been doing over the past 2 years. And it's about adapters and transformers. So what I will promise you to learn today is a brief introduction to what adapters and transformers actually are, and briefly talk about the efficiency in comparison to normal fine-tuning. I'm going to introduce to you how you can compose information of multiple tasks in a non-destructive manner, and how you can stack adapters for zero-shot transfer to unseen and low-resource languages. I'm also going to briefly walk you through our Adapter Hub ML framework that allows you to train and share adapters that you've pre-trained on multiple tasks. Some basics of what I will cover. This is all going to cover natural language processing, explicitly transfer learning. And I will only look into deep neural networks, explicitly the transformer architecture. And we will predominantly leverage pre-trained transformer-based models such as BERT or MBERT or XLMR, so monolingual or multilingual variants of this model. And these models usually have been pre-trained on massive amounts of text data using the masked language modeling objective. And usually what is done is this model is then leveraged and fine-tuned on a target task where a prediction head is stacked on top or on the output of the model. And what is usually done is that all parameters are fine-tuned on the target task. This is a bit different to adapters. And yeah, so this is the agenda. So let's actually get into what adapters actually are. So normally when we fine-tune a transformer on a target task, we fine-tune all the weights, as I just mentioned. So for example, we have our parameters theta, which are just all the parameters of the transformer. We have our data set, a specific loss function, and again our parameters, and we optimize the model such that with respect to the data set, the objective, and so on, and we fine-tune all the weights theta. So all the weights of the pre-trained model, such as BERT, are fine-tuned to perform well on the downstream task, which is named natural language inference in this case. With adapters, it's a bit different. We actually pull apart every single layer of the transformer and add new weights. They're randomly initialized. So now we no longer only have theta, but we also have phi. And these are the parameters that we've just added. And instead of fine-tuning all the weights, we freeze the weights of the pre-trained model, theta, and only fine-tune the weights phi. So now we no longer optimize theta, but we only optimize phi. And because these adapters are added between frozen layers, we refer to them as an encapsulated. And this, by encapsulating them between frozen layers, we have a number of properties that are quite interesting that we'll look into and leverage throughout all the papers that all our work that we've been doing. So let's look at this term encapsulation a bit more. So what we're normally trying to do is actually learn a transformation of the underlying model such that it's more suited to the target task. So for example, if we look at max language modeling on a monolingual language such as English or Quechuan, we add new weights, blue weights in this case, blue adapter weights, and fine-tune them on the English corpus. And we can do the same for Quechuan. So now we have blue and green weights that are specialized for the respective languages. And because the input representations to both adapters come from frozen weights, so they are, the representations come from kind of the same, from the same random weights, fine-tuned weights. And because the model is forced to learn a representation for each of the languages that are accepted by the subsequent frozen weights, we assume that each of these modules, because the surrounding weights remain the same, are roughly interchangeable, so that they learn somewhat of a comparable distribution. And so this is what we understand under encapsulation, basically that by freezing the surrounding parameters, the adapters that we add become modular, so we can interchange them and copy them around. So in the Adapter Hub framework, we allow this training of these adapters to be quite easy. So this is joint work with a couple of people from Cambridge, NYU, and DeepMind, and is building on top of the Hugging Face framework. And we have a number of pretty cool things that you can do. Let's just quickly look at it. So that it's quite easy for you to actually train adapters. So if you've been using Hugging Face until now, then it's just like 2 or 3 lines of additional code that you need to add. So these are the additional lines that you need to add to your existing code. And if you want to load an adapter, like an existing adapter, for example, sentiment analysis, you just need to add 2 additional lines of code. And we actually extract the adapter modules so that you can share them. So for example, we have a number of tasks already available. So for example, if you, I don't know, look at multi-NLI, then you can check which architecture you're interested in. So we cover most of the existing architectures. And then we provide you with the code snippet that allows you to actually add these modules. We have authors, configurations, BibTeX files of the architecture, the task, and so on. So that should hopefully get people to cite you if you use one of those adapters. We have the same thing also for languages. So similar to what I've just mentioned with English and Quechuan, these adapter modules are available for many different languages that we've been working on, and we provide them to you so that with our adapters, you can kind of extend the model to multiple different languages that it has not seen. But this is something that I'll go into detail more throughout my talk. So yeah, if you're interested in training adapters and you've been using Hugging Face before, then changing your code is very easy. Because we build on top of Hugging Face, and you can kind of use the existing code that you have. Now, instead of fully fine-tuning the model, you can train an adapter. Cool, but what is the difference actually? Like, why would you want to train an adapter? So the first interesting question is, what is the performance of training an adapter versus fully fine-tuning a model? And this initial experiment or the initial paper that proposed adapters is by Neil Holsby and was presented at ICML in 2019. And we've built a couple of different versions of the same kind of concept. And in general, the Holsby architecture has two modular components in every single layer. And we proposed a version that only has a single component at every single layer. If we compare these architectures with full model fine-tuning explicitly on the glue task, then we see that the performance is roughly the same. So some tasks, the adapters are better. Some tasks, the full fine-tuning is a bit better, but on average, the performance is more or less the same. However, we fine-tune only a very small amount of parameters compared to full model fine-tuning. So for example, if you would optimize a single model like BERT on RTE and to perform full model fine-tuning, this would accumulate to 400 to 500 megabytes per model per task. If you only fine-tune an adapter, and in this specific setting, we have a compression rate of 16, which means a bottleneck size of 48, so down projecting and up projecting these adapter components. That's the general architecture. I think I forgot to mention that. So an adapter has a bottleneck layer, meaning that from the hidden size of 768, we down project to some kind of bottleneck and up project it again. And this, by doing this, we save a lot of parameters and computation. And the best performing architecture is with a bottleneck size of 48. And it only requires you to store around 3.5 megabytes per task. So that's around 900,000 parameters. But the performance is the same. So if you would want to store 200 tasks in a single model, that it would probably roughly accumulate to the same number of parameters if you would just train BERT on 2 different tasks. So this is very parameter efficient while performing equally well to full model fine-tuning. We also have a study on the efficiency of adapters. I'm only going to briefly touch this here. This was presented at EMNLP a few months ago, 1 month ago. And yes, so basically the training of adapters is a bit more efficient because we don't actually have to backpropagate through the entire model. We only backprop through parts, and we only need to backprop into parts that are actually fine-tuned. And so training is 1.5 times faster than full model fine-tuning. But because we have additional components, these pink components, inference is a bit slower. In this paper, we propose some methods of increasing the efficiency, but I really have time to cover that right now. But the key takeaway here is that training an adapter versus full model fine-tuning is considerably faster and parameter efficient. By the way, if you have any questions in between, don't hesitate to just reach out. I don't think I have the chat open, but yeah, just interrupt me at any point in time. I have planned roughly 10 minutes in the end for QA, but I'm happy to answer any questions in between alternatively.
Sorry to interrupt right away. So thanks for the offer. I was curious about the compression rates. If you could, I lost the details there. So there are these scores where the middle column labeled with your name gives us about the same performance as the original compression and is sometimes better, sometimes worse compared to the full model. This is on which compression rate? So which
so this is 16. Compression rate is a bad term. The bottleneck size is 48. So it's basically 768 divided by 16 or 64.
Yeah. Okay. So that's the middle one, and it's the best performing that you saw. So there is like the sweet spot.
Yeah, exactly. Like the smaller bottleneck size sometimes performed on par, but there were a few tasks where it underperformed. Basically, the model would require more capacity to cover that specific task. and a compression rate of 2 or a bottleneck size of 384. So that's basically just having the dimension. That performs quite well for languages, because that languages require more capacity to be adapted to. But tasks, depending on the difficulty, I guess, perform quite well with a bottleneck size of 48.
Yeah. Okay. Thanks for the clarification. Thank you.
No worries. Okay. Cool. To understand if these modules are actually modular or not, we've kind of addressed this in the paper Adapter Fusion, which was presented at EACL this year. And this was joint work with Aishwarya Kamath, Andreas Rückle, Kyung-Yoon Cho, and Irina Gurevich. So in this specific setting, we don't look into multilinguality, but instead of multitask transfer learning. And the standard problem that exists during multitask learning is that, if we fine tune one model on multiple different tasks, then we have catastrophic interference, because by sharing all the parameters between all tasks, we do see a deterioration of performance for a subset of tasks. Alternatively, in sequential fine-tuning, where we utilize a model, fine-tune it at task 1, use those newly updated parameters, fine-tune it on task 2, and so on, we see catastrophic forgetting. That means that we forget information that was learned at earlier stages of training. And we propose to mitigate that by learning task-specific weights for every single task. And because we don't actually overwrite any information, information cannot be forgotten. And because every single task has designated parameters, the tasks can't interfere with each other. And we propose to combine the representation subsequently. So again, this is all under the assumption that this works, like that these models are modular. So basically the question is, if they are modular, then we can see positive transfer between and by utilizing these modules. If they're not modular, then this whole setup won't work. And what we're proposing to do is that, giving a pool of adapters, a pool of modular adapters, we want to leverage the stored information that each task has learned in each of its set of weights. And we do that by learning an attention mechanism. So basically, in this setting, we have 3 adapters trained on 3 tasks, and the model is supposed to select which adapter is the best adapter to solve the downstream task. So here, the input to the adapter is the same for every single adapter, obviously. And we interpret it as the query. So the query is the same for every single adapter, and the output is the key and value. So we learn a dot product of key and query, similar as the attention mechanism, which learns to weight which adapter is best suited to solve a specific target task. So it attends over all of the adapters and identifies which one it should then utilize. We find that this setting performs very well for low resource languages, explicitly ones that consist of less than 10,000 examples. But for high resource language tasks, the performance is maintained. So this is kind of what we were aiming to see, that the model kind of selects if there's important information stored within the adapter, then it will be able to utilize it. But if the model basically, selects its own adapter, then the performance should be the same. So the setup is the following: we train on 16 different tasks and have on the 16 different adapters available for these tasks. And the Fusion architecture should then select which one of those will perform best. We can look at this in a more heat mappy kind of setting. So the diagonal, so the source, the task that we're trying to solve is on the y-axis, and the adapter that is selected is on the x-axis, and these are layers, so layers of the pre-trained model. So the diagonal means that the model has selected its own adapter again. So for example, in layer 1, the argument task selects only its own adapter at this specific layer. Basically, this means that the model has not found any other task useful in this setting. It only utilizes its own adapter. So this is one of those higher resource tasks. So for example, multi-NLI always just selects its own adapter. But in the lower resource tasks, we see that they often combine multiple adapters. So for example, CB combines the representation of multi-NLI and QQP in layer 7. And this is kind of the most important aspect for me in this work, that the model is actually able to combine representations of different adapters at the same layer, meaning that the adapters are actually modular. So even though both adapters were trained separately from each other, the model is able to combine the representations with this fusion architecture. Simultaneously, if there's no information that is useful to solve the target task, the model can just select its own adapter again. So yeah, this work for me at least was the most important to kind of show that, yeah, these adapters become modular.
If I may question again, have you also considered holding out some of the tasks? So you would have no adapter for MRPC, and then you would see how it runs with the remaining adapters for the other tasks?
Yeah, so this we do have some results for that in the adapter drop paper. It basically boils down to actually also dropping out adapters, so you can prune them after training. So that works very well as well. We did try it out, and it works well for the low resource tasks, those that never basically activate their own adapters. For the high resource tasks, the performance decreases because yeah, the fusion doesn't have a lot of capacity to represent these new tasks. So that's why the performance is slightly worse if it's the own adapter isn't in the pool of adapters. Yeah.
Yeah, thank you. And the underlying pre-trained model is always BERT, right?
We have BERT and Roberta.
Yeah.
So I'm not sure which one this is right now, though.
Yeah. Okay. Thank you.
Yes. Cool. So the next setting that we're looking into is cross-lingual transfer. And this is joint work with Ivan Vulic, Irina Gurovic, and Sebastian Ruda, and was presented last year at EMNLP. So in this specific setting, what we're trying to target is zero-shot transfer to low resource languages. And what is usually done is that we pre-train a model on a multilingual model on concatenated corpora of multiple languages using masked language modeling. We then fine-tune this model on a task in a high resource source language, so for example, English, and evaluate it on the low resource target language. And this is extremely important because training data is very expensive and often not available for many languages, especially those that we consider low resource. So what we would want to have is a model that we only fine-tune on a high resource language, but are able to serve or use for all the 7,000 languages basically that exist in the world. And as probably all of you know, there have been a set of multilingual models have come out in recent times, which is MBERT and XLMR, and they actually achieve state-of-the-art results in cross-lingual transfer. However, they all suffer from the so-called curse of multilinguality, where the performance especially deteriorates for those languages that the model was not trained on or that are actually low resource. So this setting does not allow us to actually represent all the 7,000 languages of the world in a single model. And our approach is still under the assumption that due to this massive multilinguality of MBERT and XLMR, they are still the best grounds for transfer learning to unseen languages. So what we propose is MADX, which again incorporates adapters, but this time for languages, languages that the model has seen, so English and Chinese, for example, but also languages that the model has not been pre-trained on, such as Quechuan or Guarani. And we also propose task adapters, so in combination for named entity recognition, COPA, and question answering. And we assume that with our architecture, which I'll get into in a minute, by decoupling task and language specific information, we can learn language agnostic representations that disentangle these two components. Now, this is a very strong assumption, and there's been work that builds on top of that. We show that with this very simple metric or method, this already kind of works, but there are ways to improve upon this. So this is kind of the first setting, how we propose this. And how MADX is set up is that we first, in the first step, train language adapters, as I mentioned at the very start, for example, for English and Quechuan. So these are trained, for example, on Wikipedia. Now we have language-specific components that represent or that have learned these idiosyncratic information of their respective languages, whereas the surrounding parameters are again frozen. In step 2, we then train task adapters. So for example, for named entity recognition, which are stacked on top of the output of the language adapter. So these are the transformer weights. This is the pre-trained language adapter. And now we stack named entity recognition adapter again on top of the output. And because we actually want to replace this component in step 3, we not only freeze the transformer weights, but also the language adapter. This has been pre-trained in step 1, so these weights are not random. So we only fine-tune this named entity recognition adapter, so that in step 3 we can actually replace the source language adapter with our target language adapter, Quechuan in this specific case. So during training, we pass the representations through the pre-trained weights, through the English language adapter, fine-tuning the task adapter. And during inference, we replace it with the Quechuan. So now we pass a Quechuan sentence through the pre-trained weights, through the Quechuan adapter, but utilize the named entity recognition adapter that was trained in English. So thereby performing zero-shot transfer to Quechuan by utilizing the language and task adapter of English. We evaluate this approach on a number of different languages. Some of them are high resource languages that have been pre-trained on the model. So this check mark here indicates that the MBERT model or XLMR model has been pre-trained on that model, on that language. And we have another set of languages that are completely unseen by the model. They vary in their resourceness and also in their typological diversity. So we cover many different language families and evaluate the setting on named entity recognition, XSQUAD and XCOPA. In this talk, I'll only go into named entity recognition, so please check out the paper for more results on that. And we have a lot of different baselines as well, which I don't have time to cover. So I'll just get into the kind of gist of the setting. So here we present MADX Large, which is utilizing the XLMR Large model, and we compare the results on named entity recognition compared to our baseline XLMR large. And the languages become low resource from left to right or top to down. On the y-axis, you can see the source languages. On the x-axis, you can see the target language. And so, for example, this column here means that we transfer from English to Quechuan. So here, 19.7 is English to Quechuan. And the scores that you see here is the delta of the MADX, so our proposed approach, compared to the baseline XLMR. So the realistic setting is actually in the top right-hand corner. That is, we transfer from a high resource language to a low resource language. The other settings are kind of academic nature, because why would you want to transfer from a low resource language to a high resource language? And we can actually see that in this realistic scenario, our approach considerably outperforms the previous approaches. So yeah, training or evaluating and transferring from English to Quechuan with our proposed approach significantly outperforms the standard approach where you fine-tune all the weights. So the general problem that this model has is that, and this is work that was presented at EMNLP 2021, is that scripts that basically our MADX approach utilizes the vocabulary and tokenizer of the pre-trained model. So for example, if you imagine Amharic as a script that the model was not pre-trained on, so Amharic is not covered by the Ember tokenizer at all, and then we can, and if we tokenize it, this specific sentence in Amharic, even though Ember has seen many different languages and many different scripts, it's still not able to represent this language at all. So it boils down to an UNCS, a set of UNCS. So there's no way for the model to actually represent this specific sentence in a decent kind of way. And we can see this in this specific plot. So here we have languages and their transfer performance for Ember and compared to the proportion of unknowns that the language represents sentences in. So 0 means that all of the tokens of this specific language are covered by the vocabulary, and 100% UNCS means that no single token can be represented by the tokenizer. Now we can see that there's a huge deterioration of F1 performance for the languages that have scripts that are predominantly represented with UNCS. Okay, so how can we mitigate that? So imagine we have a pre-trained model. Again, we utilize a similar setup as MADX, where we have adapters, and we have a embedding layer that was pre-trained with the model and is, for example, Ember, the Ember tokenizer, which covers 120,000 tokens. So what we can do, well, we can, if we have a new tokenizer, we can kind of extract these embeddings, learn a new tokenizer for Amharic, randomly initialize an embedding layer, and just completely replace it. So basically throwing out all of this information. That means in the same setting that we lose all the information of the embedding matrix. And that's actually a problem, because depending on which model we then use, this can accumulate to roughly 50% of the parameters of the entire model. So there potentially is a lot of information lost if we just throw away everything. So the question is how we actually utilize this kind of information that we have in here. So one easy way is that actually, as we've seen, not 100% of UNCS are represented. in the vocabulary. So there's always a bit of overlap. This can be, for example, numbers, but also entities that are borrowed between languages. And what we can do is actually just copy those representations. So for example, we have the number 20 here, and I guess Amharic in this example borrows the word the, and we can copy those representations into our new embedding space. So if we do that, then we did save these embeddings, this information, these parameters, but we still lose the remaining that there's no overlap. What we can do alternatively is actually perform a decomposition of this matrix. So we matrix factorize the original embedding matrix into lower dimensional embeddings in a shared up projection. So therefore, we partially save the information stored here by having hopefully something interesting stored in the shared up projection, which can be used by newly introduced parameters. We can also extend this to more capacity by learning multiple up projections. What we need to do for this is that we have we split the original embedding matrix into specific groups. We can do this, for example, by k-means clustering. So we k-means cluster the original embedding space into k clusters, or we can now actually learn this end-to-end by actually, predicting the output, but having something like a Gumbel softmax which routes the which learns to route the embeddings to a specific group automatically. We test out both things, and actually they perform more or less on par. We can briefly look into the k-means clustering. Well, okay, something happened to my screen. So this k-means clustering setup is quite interesting. Here we have actually 6 clusters, because 5 clusters basically look like the first one here. And what you can see here is the clusters that of the original mbert matrix that the model automatically learns to split each token in. So we've split the groups by script, and we can see that 5 clusters basically consist predominantly of Latin tokens. And that makes sense because roughly 90,000 of 120,000 tokens are Latin. So it makes sense that a model automatically learns to cluster them, the Latin scripts, together. We find that there's a Cyrillic cluster, there's 2 Chinese clusters, there's 1 cluster that consists of many different scripts, but no Latin, and there's 1 cluster that is split more differently. So what we can see here is that there is probably some kind of information that it's good to combine or to give more capacity to, so that the model can group basically those tokens that are somewhat similar together. So now that we've learned lower dimensional embeddings and multiple shared up projections for each of these clusters, we can also combine this with this lexical information. So basically, we no longer copy the higher dimensional embeddings, but instead the lower dimensional embeddings into our now lower dimensional target embedding layer. We copy the shared up projections that are shared between, that have been learned for each of those clusters. And the only thing that we need to do now is learn a routing mechanism for which embedding should utilize which shared up projection. And we do this end-to-end using a Gumbel softmax. So basically the model is again trained using masked language modeling, similar to the MADX approach, but now we have this this initialization and newly introduced embeddings, and which were frozen. And in the MADX approach, we just used the mbert tokenizer and embedding layer. Now we have a new designated embedding layer for each new language. Okay, so we evaluate this from a number of source languages. They're typologically quite diverse: English, Chinese, Japanese, and Arabic. We transfer this to a set of seen languages, but that are underrepresented in the MBERT tokenizer. So Georgian, Urdu, and Hindi. We have a set of unseen languages, but whose scripts are covered. So for example, Wolof, MBERT has not been trained on Wolof, but Wolof is written in Latin. So this is a unseen language, but with a seen script. And lastly, we have a set of languages with completely unseen scripts. So those, as you can see here, the proportion of UNCs is very high. So the model is not adequately able to actually represent those languages at all. So these are the three groups that we evaluate on. And we perform experiments on NER and universal dependency parsing. I'm only going to look into NER, check out DP in the paper. So just again, kind of comparing MBERT to MADX, we can see that for for all settings, the performance of MADX outperforms MBERT. However, both approaches fail miserably for unseen scripts, which is due to the case that both models use a tokenizer that is isn't able to represent those tokens at all. Okay, so now if we have this approach where we don't do the lexical overlap, just the shared up projection, so just learning like this matrix factorization, but no lexical overlap, we see that for unseen scripts, the performance dramatically improves. But it's a bit worse than for the unseen and seen scripts. If we then combine this with the lexical overlap, so sharing the up projection with the lexical overlap, we actually see even better performance for unseen, and even get a slight edge over seen and unseen languages compared to MADX, which indicates that actually the unseen languages profit from these latent concepts, and by because the languages have been underrepresented in the pre-training, having a designated tokenizer actually improves performance, even though the model has seen that language before. Cool. Now, let's go to some works that are currently under review. So this is work that I've been working on during my internship at FAIR, and it builds on all the work that we've been looking into, because previous work in adapter settings, as I've been talking about for a while now, utilizes a model, a transformer-based model, and then adds adapters to it while freezing the surrounding parameters. So here we have these adapter modules added post hoc. In our newly proposed XMod approach, we actually pre-train these modules from scratch. So we make the model modular during pre-training, so that during fine-tuning, the model is kind of already prepared to see new modules, such that it isn't kind of confused. And our hypothesis is that because the curse of multilinguality has already kind of messed up the model at the start, just adding these adapters post hoc tries to mitigate a lost cause. So by making the model modular from scratch, the performance will actually improve, and we might be able to lift the curse of multilinguality. So that is the question of this entire work. So does this modularity during pre-train actually lift the curse of multilinguality? So our baseline here is a standard multilingual model such as XLMAR, where all the parameters are shared, versus a modular version where we have language-specific weights during pre-training. And we have a very similar architecture. It's slightly different to the architecture that I've been talking about earlier, due to some problems during pre-training of the other variants. But as you can see, we actually have a shared component here for a number of reasons. And yes, so the shared, what we aim to do is basically have a very fair comparison between a modular model and a fully shared model. And then the question is, what happens if we train on multiple different languages? So if we slowly increase the number of languages, what happens to the model? Which is basically, the curse of multilinguality has shown that the more languages we add, the worse the performance gets. Now, is that the same? Does that also is that also true for the modular version? And some important hyperparameters that are maybe a bit boring, just I'll just walk through them briefly. So each module consists of 7 million parameters per language. And for fair comparison, we don't have the standard architecture, but actually one that has one in the non-modular version, so the fully shared model, we have one modular component that is shared between all languages, so that both models have the same number of float point operations. So in the forward pass, both models have the same number of operations to make a fair comparison. So the non-modular model shares all the weights between all languages. So it's 270 million parameters, and per language, we have 7 million parameters added, whereas the shared model has 277 million shared parameters because it has one module added.
Sorry, a quick question. It's great that you did this fair comparison, so that you added these extra parameters to the fully shared model. I guess the performance was identical. It didn't improve the shared model, or did it?
You mean, so the performance between
the very baseline, the unfair baseline versus the fair baseline.
The performance was basically the same.
Thank you.
So then the question is, how do we add more languages? In the paper, we have multiple different variants of that. It's accessible over open review. But the most important experiment was that I wanted to identify that each model has seen the same number of examples in each language. So for example, if we start with 13 languages, we define that we're going to train for 125,000 update steps. So when we train for 30 languages, because we're now training on more languages, so that the model sees the same number of examples in each of the initial 13 languages, we have to increase it by 70,000 update steps. So we calculated how many examples the model has seen in each of these 13 languages when we train on 125,000 update steps, and increase the number of update steps respectively, such that the comparison remains the same for the initial set of languages. So we also train another model on 75 languages, but that's actually missing here. I think it's 270,000, so not a lot more update steps. So first, let's look into the perplexity. The blue lines indicates the modular version. The orange line is the shared model. Y-axis is the perplexity, whereas the x-axis is the number of languages that the model was pre-trained on. And again, all models have seen roughly the same amount of examples in each of those languages. And we can see that the shared model's perplexity increases quite dramatically with the number of languages that we add. Higher perplexity is worse. Whereas the modular model actually maintains the perplexity, and for some languages actually improves. So that's kind of interesting that there seems to be a positive influence between languages, even though the model has not seen more examples in those languages. And this is kind of the first indication towards that the curse of multilinguality is lifted, because the perplexity is an indication for the model's ability to represent the respective language. Okay, but what is the performance on a downstream task? And the downstream task performance is evaluated on XNLI and NER. We also have XSQuad and MLQA results in the paper. And in general, what we can see is that, again, I actually forgot the labels. So blue is again modular and orange is the shared model. And we can see that the modular model improves over time or over the number of examples, whereas the for XNLI and NER, whereas the non-modular model decreases in performance, which is again what we expect from the curse of multilinguality. So this indicates that even though the model, so there's like two really cool things about this. The first one is what we would have been happy with is if this line is kind of the same, right? That would already indicate that the curse of multilinguality is kind of mitigated. If the performance, independent of how many languages that we add to the model, the performance just stays the same. However, even though the model has not seen more examples in each of the target languages, the model improves. So this indicates that there's a positive, not only is the curse of multilinguality mitigated, but there's positive influence between languages. There is some instability if we trained on too many languages, which is kind of interesting here. And there's a drop in performance between if we don't train on a lot of languages. We have some experiments regarding this specifically in the paper, where we see that if we don't train on a lot of languages, we need to train for a bit longer so that the modularity starts to kick in. So then this drop in performance or this performance difference is also kind of mitigated or closed. Yeah. The second experiment is what happens if we add languages. So is it important to pre-train on a language, or is it okay to add one in the second step? And so in step one, we train to kind of evaluate the setting. We pre-train 2 models on 2 sets of languages. And then we add to each of the models the languages that it has not seen before. And this setting is again similar to what we've done in MADX. So we, fine-tune a new adapter on each of those target languages. And then we compare the performance. And these are the results. So blue is a language that the model was pre-trained on, and orange is when the language was added. So this is model 1, and this is model 2. And respectively, the other language was always added. So as we can see, the performance is more or less the same. We even see insignificant gain in performance for the languages added. So this shows that, in fact, adding a language to these pre-trained models does not we don't witness any measurable drop in performance, at least for XNLI. So it doesn't matter if you pre-train on the model or if you add the language in step 2, which then shows that these models can actually be extended to all the languages of the world, even though we've only pre-trained it on a small amount of languages. So we argue that the curse has been lifted by adding a small amount of language-specific capacity to the model. We mitigate the catastrophic interference between languages and additionally improve per language performance. And this setting allows for languages to be added post hoc with no measurable performance decrease. Okay, so we have another paper under review which looks at all of this in a multilingual, multimodal setting where we have a new task. I'm not going to have time to actually look into this right now. It kind of extends the whole idea to multimodal settings where we split text and images with adapters. And we have a cool new data set for that, which is cross-lingual general question answering. So please check that out as well. In general, what recent research has shown is that, or a lot of interest has shown, is that modularity is on the rise. There have been a lot of different adapter architectures. There's for adapters, which is diff pruning, where they only identify weights in the model that have to be fine-tuned, whereas the surrounding, like majority of parameters are just frozen. There's bit fit, which just fine-tunes the bias terms. There's prefix tuning, which adds embeddings or smaller components around the multi-head attention. There's work that actually combines adapters with prefix tuning. In machine translation, adapters are super relevant, which has started by Bubna et al. In 2019. There's been denoising adapters at EMNLP right now. These are just a small number of papers that that I had time to talk about here right now. Hypernetworks or contextual parameter generators for adapters are super interesting. In the first paper by Üstün et al. At EMNLP, we presented a similar paper at EMNLP 2021, which is called MADG. There's so many open questions, like how do we increase the modularity of adapters? How do we train domain-specific adapters, et cetera, et cetera. So this is, in my opinion, a really exciting direction. So yeah, I hope that these pointers help you in your work. There's a lot of generative adapter possibilities as well. So the key takeaways of my talk today are that adapters actually train faster while maintaining the performance. Adapters are modular and they can be stacked and combined for zero-shot transfer to unseen languages, but they can also be composed to combine the information. And adding language-specific capacity to the model during pre-training, at least we argue, lifts the curse of multilinguality. So thank you very much for listening. Yeah.
Well,
there are any questions?
Yeah. Thank you very much for giving us the overview of your recent research. I think it was rather interesting, especially of many of the people who listened to your talk. There were some questions already during your talk, but now the floor is open for more questions. Please just talk if I don't see you or don't call your name.
Okay, if I may.
Yes.
Okay, there was someone else who wanted to ask questions, so please start.
Yeah, okay, so I will start. So my question is about the position of the adapters inside the transformer. Like on all of the images you were showing, the adapters are after the feed-forward layer. Like, did you examine like positioning it before the feed-forward or somewhere inside the attention heads?
Yeah, good question. So the original paper by Holsby et al. Actually has one right after the multi-head and right after the feed-forward. And if you just have it right after the multi-head attention, the performance is very bad. So in this adapter fusion paper, we had a huge grid search around how to actually like what architecture is the best, like the placement, and we found that the most important part is right after the feed-forward. Prefix tuning, like check out, it's a paper by Graham Newbick's group. They have a lot of new ideas. Let me just point you to that. They have some new, very cool evaluations on how to, oh, this is the wrong one. So yeah, this paper here combines prefix tuning with adapters. It's great. It's a really cool paper. I'm 100% sure that it'll be accepted at iClear. So check this out. They have some additional pointers how to close the gap between full model fine tuning and adapters even more.
Yeah, thank you.
So yeah, so I want to thank you for the talk. It was very interesting. And my question is whether you tried or whether do you know about the related work that considered replacing the feed-forward layer with the adapter layer and trying to learn the combined effort of the adapters during pre-training and then trying to adapt this feed-forward layer on the downstream tasks or during the fine-tuning, because by design they seem quite similar, right?
Yeah, I mean, so yeah, so this paper here, I guess, kind of goes in the direction that you're asking. It's a mixture of experts approach, similar to switch transformer, and they actually, let's see if they have a figure. No. Anyways, what they do is they do more or less what you just proposed. I think they have a shared multi-head attention layer, and for every single expert, basically, they have a specific feed forward component. So this is an expert. There's no, the only set of shared weights, as far as I remember, are the multi-head attention. The problem here is that if you scale this to many different experts, then your number of parameters explodes, similar to demixers. And what we've kind of tried to do is have the majority of parameters shared between tasks or languages or whatever, and only a small amount of parameters that are language or task specific.
Okay, now that you mentioned the mixture of experts, there's a follow-up question. If I understood correctly, in all your models, you were basically combining the modules or the adapters using the mixture, right? Or did you do some hard combination by masking out some of the non-desired adapters?
Yeah, so none of my work has utilized this mixture of expert settings. So in the adapter fusion setting, where we kind of learn which adapter is the most useful for our downstream task, this is kind of the only mechanism. Like the model just assigns very low probability to each of the task adapters that are not utilized at all. That's the only paper or work that I've been working on where I combine the representations of multiple adapters. In the other settings, it's more like passing through, parts of the model that we know come from, are like learning a specific, data source. So for example, we know that this is an English sentence, so we will pass it through an English component. So there is no kind of learning in what expert this model should pass through. It's that we know where it comes from, and therefore we pipe it specifically through that component. So there's no learning necessary in this specific setting.
Okay, so I don't know if there are no other questions from others. So may I have one more question?
Yes, sure.
That is, yeah, you mentioned your work where you were doing, training the adapter choice using Gumbel softmax for what is it called? So you can derive the function and properly backpropagate, right? So did you, during inference, do you do the argmax or do you still perform the softmax operation?
No, like, this just has to be learned once, and then you can kind of mask out everything else.
Oh, okay.
Yeah.
Okay, thank you.
So are there some further questions? Just speak. I can't see any.
Yeah, so
yeah, Andrzej, please.
One more question from
yes,
me. So
please.
thanks for a nice talk altogether. I was curious, the underlying model that you then repurpose for the different tasks through the adapters, how critical is that? So in your experience, you've mentioned Bert and Roberta. Have you also in other in previous years or so worked with other models, and have you worked with smaller birds and larger birds? How is that important for the final performance and for the robustness of that method?
Yeah, good question. So like if you just use encoder models, the performance is the same for large, base, even distilled models. We cover all of those architectures in the adapter hub. So it doesn't improve, it just maintains performance roughly. For multilingual models, it's the monolingual performance is slightly worse. So for monolingual models, the performance is roughly the same. We do see a small gap for multilingual models. That's a bit interesting. It's smaller than, but and it might also depend on the task. So we've worked on named entity recognition, and I haven't in multilingual settings, but I haven't worked on named entity recognition in monolingual kind of settings where I just fine tune like Bert on Connell 2003 or something like that. That's not so I'm not sure if it's task dependent or multilingual model dependent.
Yeah. So just if I understand correctly, if you start from a monolingual model, the performance is slightly worse, and it regardless if the task is then in multiple languages or across the tasks, right? So starting from a monolingual, no. So what is the claim?
So so the monolingual models, if just Bert or Roberta, if you use those models, the performance with adapters is more or less the same. On glue tasks, there's so many tasks that I don't know the performance of all of them, but if you look at glue tasks, then the performance between adapters and fully fine-tuning the model is the same. If you look at the scores of, for example, WikiAn in an MBERT setting, so WikiAn is a multilingual and named entity recognition task. There we did see like a 0.5 or 1 F1 point worse performance if we use adapters with MBERT compared to to MBERT without adapters.
Okay. Yeah.
But in the crosslingual setting, the adapters were better, like considerably better. So it's a completely different setting that we evaluated on until now. But yeah, so in cross-lingual settings, the adapters are good. Yeah. Then I guess there's the second question on like generative models. There the performance is a bit worse. So we worked with GPT. I think we had some summarization tasks there. The fully fine-tuning was better. We had some also summarization tasks with BART. There the performance was, I think, similar. Yeah, we have a blog post around generative and sequence-to-sequence models on the Adapter Hub. So I didn't do that. Some students did that. So check that out for more information.
Yeah. But if one wants to start with this, then essentially the choice of the underlying model is not that important. You can throw in adapters to any transformer architecture pre-trained for essentially anything, and it will do the job.
Yes, exactly. Yeah. And any task, machine translation, summarization, classification tasks. I think generative models are like the go-to direction for adapters, because there you have domains and tasks and languages. So I think that's, I haven't done work on any generative settings, but yeah, like if you're interested in adapters and you're working on generation, you should definitely check out adapters. There's a lot of potential there.
Yeah, thank you.
Thank you. I can't see any hand and no voice. So let me thank the speaker for his interesting talk. I think the discussion was also very rewarding, so to say. And I only may hope that we can see you in person once the restrictions are over. And when I speak about restrictions, I have to say that we had to cancel our seminar next week because the speaker cannot come in person and he would like to be here in person. So we may hope that the situation might improve in spring. I don't know. And he will be here and give his talk. So our next meeting is in 2 weeks on Monday the 13th, when we have a longer meeting. It's a workshop or seminar in memory of the late Professor Peters Gal. The program is on our website, and I can recommend you to be online with us. It will be a totally online seminar, and the speakers are very interesting people, top people in different domains. So hope to see you in 2 weeks, at least through the screen. Thank you, and have a good time. Bye.
Thank you. Bye-bye.
Bye-bye.